Welcome everybody to our first seminar of the second half of the semester, the spring of 2019, and it's my pleasure to introduce Professor Greg Tripoli, who will talk to us today about aspects of his work on tropical cyclones. Greg has been in this field for a very long time, and you know, when I think about people who know a lot about a lot of different things, the first person that comes to mind is Greg Tripoli. He could talk about just about any subject at a level that you just can't even fathom most of the time, and I literally mean that. He'll come in my office and say, have you been thinking about this? And I'll say, yes, Greg. And he'll stop to tell me some things that I have no idea what he's talking about for a while, and then a month or so later I'll realize he was exactly right about all that, and I'm glad he got me thinking about it. And it's been my great fortune to be next to somebody who prompts you like that for 25 years. So I've had 25 years of constantly being told, rake over what you know, and think about it in a different way in so many words. It's been great. Greg joined the faculty in 1987 after securing a PhD at Colorado State in a somewhat unorthodox manner, I think it was fair to say. Wasn't it something along the lines of you built the RAMS model after you built the GFD hurricane model, and Bill Cotton thought it would be a real shame if you didn't get a PhD?
No, it wasn't quite like, no, I went over there, see, I had built the GFDL hurricane model, and then he recruited me to come and build his model.
Right, that's what I thought, yeah.
But the terms of my recruitment is that when I get it built, I can write something up and get a PhD.
Oh, I didn't know that. Okay, so this was a
that was the terms of my movement.
Yeah, okay.
Because I liked it at GFDL.
Okay. So anyway, that's how Greg got his PhD at Colorado State with Bill Cotton. And he's been in our department since 1987 and working on hurricanes and mesoscale weather systems, large-scale circulation, just any number of issues, as I mentioned before. And at a level that's right at the front edge. And of course, built the non-hydrostatic model here, UW non-hydrostatic model, which a lot of people use here as a tool for investigating all manner of scale of phenomena, all the way down to the 1 meter resolution, remarkable stuff. And he can't leave his model alone. He rebuilds it, he parallelized it in the late 90s, early 2000s, and there was never really a so-called frozen version of NMS for a long period of time. I mean, half my career the thing was in flux, because he just can't leave it alone. He built his own house. He's done that more than once. So he's one of these Renaissance people who just can't stop tinkering with things and making them better, and that's why it's so exciting to work around somebody like this. And he's just for the last 3 years spent time making our department better as chair with a flurry of excellent hires and organizing all of that. So Greg's a real Renaissance man. Today he's going to tell us about energetics of tropical cyclone outflow, undoubtedly in language that only Greg has been thinking about for the last few years, but soon enough everyone else will adopt it because that's just the nature of his thinking. So Greg, take it away.
Thank you, John. Well, what I'm working on here is no exception to tinkering with the model, because what I've done now is I tried to examine the energetics of a tropical cyclone by going into the non-hydrostatic model and sifting out the actual tendency terms inside, second by second, and watching the evolution of how energy is transferred, and actually come up with some conclusions on that. So it's a very intense energetic study that we're about to look at. I want to acknowledge Pete and Will. Pete helps me get all the data that I use. I've done in this talk here, I have at least 13 hurricane simulations plus some other stuff. And Pete always retrieves the data for me when I need it. And Will has worked with me on looking at observational data that we took during the TCI field experiment and helping me put it in a form where I can compare it to what the model simulated. So, thank you to both of you. So the big question here is, how does the outflow environment of a tropical cyclone encourage its formation? And then how does a tropical cyclone affect its environment the other way, and ultimately affect other kinds of weather? And then finally, are TCs an important or necessary part of the general circulation? And there's been some discussion of this on the tropical list. And I think the general feeling is that they're not really important. That mainly what they do is mix the ocean temperatures downward, ocean heat downward, and that enhances vertical or meridional transport of heat in the oceans. But what do they do to the atmosphere? It's another question. Well, the current state of the art is we recognize the hurricane as a self-contained circulation where we have a 4-branch Carnot cycle. And what's interesting here is the cooling branch of the outflow. The outflow moves up and then it cools over time in this branch over here that allows the flow to get down to a low enough level. And this is probably not realistic. Probably the level it has to get down to is much lower than this. But you have to have sinking motion to compensate for the upward motion that's driven by radiative cooling. So where, relative to the storm, does this subsidence actually occur? This is all kind of details left out of the theory. And the adiabatic descent of convective downdrafts, again, is between the theta minimum level and the surface. So that's down around 700 millibars where this begins. So this is quite a distance that this cooling has to go on. So what do GCs do? Well, we know they mix the ocean, and the frictional exchange with the water is important for ocean mixing as well. Mixing. Again, this is not a major or necessary part of the global circulation. So in many ways, when you look at what it does in this sense, you can take it or leave it. You don't have to have a tropical cyclone for any reason. But what do they do to the atmosphere? And this is where we don't find, do they stabilize the atmosphere to conditional instability? No, it's still conditionally unstable after they're finished. Do they overturn baroclinic energy? No, that's what an extratropical cyclone does. In fact, tropospheric stability remains conditionally unstable and seems to be altered surprisingly little after tropical cyclone goes by. So what do? Well, this statement is except in the UTLS, the upper troposphere, lower stratosphere. They change things, and they change things dramatically up there. The total mass of moist entropy that TCs deposit into isentropic layers of the upper troposphere, lower stratosphere is huge. It's not just a little. I'm going to show you that one tropical cyclone could put as much mass in the tropical bubble as is up there when this tropical cyclone started. And this is anomalous mass, compared to an extratropical sound. So you know the tropical tropopause is raised and there's an extra amount of mass in there. One of these tropical cyclones that's strong could double that mass. One. Typical outflow is about 360 K. This is the upper UTLS, and I call the upper UTLS the 356 K to 410 K. And this is in the overworld of the tropics, because once the air is put up that high, it can't come down again in the tropics. And that's because of this. This is a meridianal plot for December 1st of 2016, but they all look the same, of the net radiative heating over a 24-hour cycle. Or it just actually is at a given time, but it's different periods around the globe. But what we see here is there is this height here of about 356 Kelvin. We're above that level in the tropics, which go from about 30 to 30 here. In the tropics, above that level, there's no radiative cooling. In fact, there's a little bit of radiative warming. So nothing that's put up in this level above 356 K can come down in the tropics. The only place it can get radiation so it can subside into the troposphere is it has to go to the extratropics, because over here, the level of zero net radiation, there is none. It's cooling all the way up. So once you get to a latitude much higher, it can cool and complete the cycle. So that Carnot cycle, as shown by Emmanuel, can't occur in the tropics. It has to extend into the extratropics if mass is deposited in this white area. So therefore, this model cannot work in the tropics. This stuff over here has to be occurring in the extratropics where there's radiative cooling that will allow that to occur. And the outflow will remain on isentropic surfaces as long as it's there. What it can do is it can get some diabatic forcing from the warming that may raise it to a higher surface, but it can't get down to a colder isentropic surface while it's in the tropics. So I've looked at JAPE before, but interestingly, JAPE is made up of an atmospheric density anomaly, which can be translated into a mass anomaly. So compared to a standard sounding, the amount of mass in a given layer of the tropics up in the areas where there's positive J is actually greater than it would be an extratropical sign. So there's a mass anomaly which we can equate to the available potential energy by this GZ, the height. And interestingly, tropical cyclones don't really change the height of the isotropic layers up at higher levels very much. They just pump more mass in those layers. And they change a little, but not a lot. So, what do they do to the environment? They raise the tropical tropopause a little bit more than it already is raised. And they contribute to the UTLS mass anomaly that forms the J bubble. The available potential energy of this mass anomaly, available relative to an extratropical sounding, using standard sounding as a measure, must travel to the extratropics to be resolved because of this level of zero net radiation. The bubble also, expanded layers up there, contains low potential vorticity. It's in the tropics, so Coriolis is already low, at least vertical component Coriolis. And the stability is weakened some by stretching the isotropic layers and pumping them up with more mass. So if you just take a cross-section through the tropics, it looks like this. You have isotropes, and this is where the J bubble would be over here. This is latitude going from 90 north to 90 south. This is an actual case here. But what we see is this blue line here is the approximate height of the tropopause. And you can see the tropical tropopause is elevated because it kind of draped up somewhat over this J bubble. The J bubble kind of pumps it up. So if you pump more mass into here, you effectively push up the tropical tropopause even more. And the effect of that is this bubble keeps building up mass, and eventually, or over time, it lets mass into the extratropics via tropical plumes. This is what the bubble looks like across the entire globe. This is a map of the Earth. Here's North America, Asia, and so on. Europe is up there. These are just cross sections I put through it. But you can see this bubble extends over the tropics, and it has little protrusions that come out where it's sending tropical bubbles of this mass into the extratropics to resolve the anomalies that are in the tropics. So the outline of what we want to do is look at a working hypothesis, look for qualitative evidence with stuff from Will, supporting qualitative evidence qualitative evidence from a simulation, then some supporting evidence from Will, and then look at some of these energy transfer metrics and some of the actual results, and make some conclusions on that.
Excuse me, Greg?
Yeah.
So we talk about the resolution of the outflow having to go to higher latitudes to that before it can begin descending. Isn't there like a radiated flux divergence at the top of the cirrus that's in part of the outflow layer that can help with some of that cooling?
A little bit, but it's not enough to do anything. Yeah, that's in the model, and the model shows it's relatively minor. In fact, the radiative transfer levels are surprisingly minor, whereas a radiative flux would be on the order of 100 degrees per day cooling at the top of a cirrus anvil. The amount of mass you're putting up there in terms of its energy is equivalent to about 1,000 times that amount of cooling. So it's overwhelmingly greater than the radiative cooling. Now, as I said, the radiative cooling tends to match the temperature change in those layers a little bit. But the actual mass that's being put into those layers is the big thing here. So you got to separate your concept of temperature change from mass change. So the mass that you're punching into a layer is expanding the layer that's holding this mass. And that's the important thing here. Yeah.
If I could just ask a little bit about J and the meaning of it. So by defining it rho prime over rho G, that's like minus the vertical acceleration due to buoyancy in the Boussinesq form, just times Z. That's kind of interesting. Does the J bubble, by being rho prime positive, mean it's colder than everywhere else at that same altitude? And so it's actually going to want to slide downhill.
It's actually not. In the calculations I'm doing, it comes out to be probably a little warmer than the surroundings. And so as a result, the geopotential height of the layer is actually suppressed a little bit inside the low. So it's reverse of what you would think, but it can go in either direction. It's very tiny compared to the amount of energy put up there in terms of the mass that's up. So the actual geopotential doesn't change much, the temperature doesn't change much, but the mass up there changes a lot. And also associated with this mass deposition is a deposition of a lot of low potential vorticity. So I look at a qualitative thing to kind of demonstrate what I'm doing here. I'm going to use the model to simulate Patricia. And the way I'm doing it is because I want to simulate these things, and I got like 13 simulations that I probably won't be able to spend time on all of them, but the simulations all look like this. They have a 3-grid system. The outer grid is a very regional, global scale grid. The second mesh is about 1,000 kilometers across, and this is what I call grid 2, and this is where I'm doing all the energetics calculations. And then grid 3 is where the storm is on the inside there and resolves the storm. With about, in this case, I'm running 1 kilometer resolution, but most of the simulations I'm running are 2 kilometers resolution. And it's enough to be at least cloud representing to some extent. Then this outer region, these circles out here, are where I relax the solution to the GFS or the ECMWF, whichever one I'm using. The blue line is the last area. This is a 3,500 kilometer radius from the center here. And this is where I maintain whatever the model solution is in here. That's what I'm doing at the blue line. And we're on the green line, this is going to be strictly the GFS solution. So I relax from the model solution to the GFS solution from 3,500 kilometers to 5,000 kilometers away from the storm. And that keeps my large-scale flow pattern realistic, because it's hard to go 7 days and keep anything realistic to run a storm. And then the second thing I do with the storm is I keep the storm in the inner grid, and I put down the coordinates of where the storm actually was, and I keep repositioning the storm if it moves away, using a technique developed by Shui Chen with the MN5 model, should be that way. But, what's that?
It's two-way nested?
It's two-way nested, yeah. But the grid positioning, you pick up the inner nest and just move it, and then let the boundary conditions sort themselves out. And as long as you're not doing that too quickly, it doesn't seem to affect too much. Yeah.
That GFS solution you have on there is actually the GFS analysis every 6 hours.
It's
right?
actually
not a
the analysis.
GFS run for 7 days.
Right, it's a GFS analysis, that's right. So that's the real, what actually is happening out there, as far as the analysis can determine from the data we have. So let's look at Hurricane Patricia. It's one of the most intense storms ever. So this is just looking at the rain field at the surface, showing you that there's a lot of structure in here with a 1 kilometer resolution. And I can point out, so it's going through an entire life cycle. The storm develops, and then you'll see it make landfall. It forms an eye. It has rain bands and intense eye wall circulations that form within it. And from the upper right, you'll see the topography start to come in where it's going to make landfall. Takes a little while to look at all this, but that's a very nice storm here. It's about this, it's like in the 880s, just like the actual storm was.
What are the colors?
How intense, it's like a radar echo. So it's how intense the rainfall is. And so here comes the land, where it makes landfall. What's your business? Okay. So that's an example of the simulation. Now this is looking at the simulation with the surface theta E, and you can see it spiraling in. I don't want to spend too much time on these guys. There's anything to look at here. But the one thing I want to point out here at the theta E, and of course the brighter colors are the higher theta E's, is you'll see the highest theta E's in the eye wall. And this is a very unique thing about hurricanes. Hurricanes produce very high theta E in the middle because of the low pressure. The low pressure makes the relationship between sea surface temperature and actual theta values that can develop at the surface much, much higher for theta because the pressure is so low. And you can see these very bright yellow areas forming here around the eye wall. That's having theta E that's 10 degrees at least warmer than the theta E anywhere else around it. So it's manufacturing extreme values of theta E. Now you can look at this in the vertical, and this is quite interesting. I just highlighted in yellow that theta E. Now watch how you can see the assembly line, or what I want to see, conveyor belt of theta E as that forms. You can see the conveyor belt going up to the tropopause. So this is a cross-section through the eye wall. You can see these two yellow branches. It's a circle, but these two yellow branches, and it's a circle at the surface. You can see that being transported up to that yellow layer as it becomes equal to the theta in that yellow layer. So this is quite intuitively nice that you can see this happening here. So right now you're seeing these two, sometimes there's an eye wall replacement in there, but you see these in the eye wall, you see this conveyor belt, a very high theta E just going right up into the tropospheric layer. See how that's happening?
Yeah,
It's pretty
choice.
It's pretty amazing.
Is that depression, is that, your color scales, is that higher theta E?
Yeah, the yellow, I emphasize the yellow because
I'm
that's,
talking about above the yellow at the top.
yeah, that's all higher up there, yeah. I just emphasized that one area so you can see the conveyor belt. So when you look at this, what you're actually looking at is the level, region 2 is this region 2 over here. Region 1 is this region in here. Near the surface where you're manufacturing that theta E, and then it goes up. Where is region 3 or region 4? It's not on this picture. It's somewhere else. And it can't be in the tropics. So, summary, this is kind of the cartoon of what everything is looking like. You have the overall circulation, then you have these enhanced circulations going up these conveyor belts. And the strongest vorticity in the system is here. The strongest vorticity in the hurricane is derived by the surface friction, which produces strong vorticity in the boundary layer from the friction, and then that's carried up in the storm along these lines here, which is actually a circle, and then deposited out here in a tropopause, or in this outflow layer. And as you can see, I've indicated the outflow layer is a little thicker here, and then it thins. The outflow layer has these bulges in it containing this theta E energy. And once you put it up there, there's no diabatic process that can change that theta E. It's conserved. It's going to go until it gets to the extratropics, or maybe it rises up a little bit from radiant warning. So let's look at supporting evidence for this from field campaigns. Here's isentropic thickness, and these are plots that Will made. And you can see from here the isentropic thickness is enhanced in these layers. It's lower here, and then it's enhanced right around 360 in all these different flight trajectories through storms. So this widened, enhanced thickness layer is up there just like the model showed. And we can look at potential vorticity, trying to calculate. We only have a single two-dimensional flight trajectory, but we can just look at the stability and estimate the potential vorticity strictly from that. And you see these blue lines over here right around 360, which represent the low potential vorticity minimum that's in the outflow layer that's coming out. So it pretty much matches what the simulation was doing in that sense. So let's look at the metrics of some energy transfer. The types of energy we have are thermal energy, like molecular motion type, and enthalpy versus internal energy. We're going to use enthalpy, of course. And we have free energy, which is entirely related to the compressibility of the atmosphere, and so pressure. So R log P would be the free energy. And we have potential energy, which is geopotential, potential energy, latent heat, different kinds of potential energy, inertial potential. When you have a storm, you move the air out from the middle. There's a certain potential energy between the outside of the storm and the inside of the storm, wanting to make the flow go back in. kinetic energy, but here's a energy budget diagram, which if I spend time on this, will be done. But we basically have moist entropy in this red box over here. And moist entropy is only changed by diabatic processes. And by diabatic, I don't mean moist adiabatic, I mean real diabatic. Moist adiabatic processes exchange latent heat and entropy. But entropy, which is related to theta E, is not, is only affected by diabatic, real diabatic processes like radiation or surface fluxes, truly energy that goes in through the sides of the box. And then up here we have free energy, which is the log P, compressibility of the atmosphere. And you get some kind of a relationship between this free energy and equation of state that it produces a relationship. So if you raise the temperature, this will go up and this will go down if you don't change the theta. So you can adjust the relationship between pressure and enthalpy without changing the entropy, which is only affected by radiation and surface fluxes. So above all this free energy is the energy that can produce work. In the equations of motion, there's only pressure that accelerates flow. It's the only thing that can do it. So it's the movement of this piston up and down here, free energy, that's doing work on the environment. It could be lifting air up, but it could also be accelerating air. And so this free energy is expended through this kind of like a piston here to increase kinetic energy, or I have inertial potential energy, which is the amount of kinetic energy that's balanced against the pressure gradient force. So that energy becomes unavailable and balanced. You also have hydrostatic balance in the vertical between geopotential and hydrostatic, or geopotential and vertical pressure gradient. Now the free energy, as a parcel rises, is consumed and changed into geopotential energy. But it doesn't change the entropy. So as a parcel rises, its moist entropy remains constant, unless you have a diabatic process like mixing or something. And there's surprisingly little mixing in hurricanes, laterally, because of the inertial resistance against lateral motion. So this goes right up into geopotential. So what is going on in a hurricane is we have high theta E down here and high theta up here. The entropy is pretty much the same, going from the surface all the way up. The entropy doesn't change, the moist entropy. Does that make sense? It doesn't change, it's conserved. Only surface fluxes that build it up at the surface, and radiation, which is way too slow to make a difference. There's nothing to change the moist entropy in the upward motion of a hurricane. It just goes up. So that's what we showed with those yellow streaks going up. When the entropy is manufactured near the ground, and it rises in the plume, and then goes out, and doesn't change. It just goes out with that same entropy. What has changed? If we did all that work producing geopotential energy and making the storm move through the kernel, where'd all that work come from if we didn't change the entropy? Where'd it come from? Anybody know? It's the free energy. Because when I lift the parcel up there, the pressure is now like 50 millibars at the top, or 100 millibars. So the pressure's gone down tremendously. The free energy is gone. This is Gibbs free energy. It's consumed that free energy to perform work. And most of that work is stored in the geopotential. So what we want to do in the model is we want to look at entropy budgets and energy budgets, and this is, it makes no sense for me to spend much time on exactly how I'm doing this, but if anybody wants to know later, I'll explain it. So There's a thermal energy budget. Adiabatic flow must move along its matching isentropic surface, unless it is a diabatic process, of which there's few. The thermal energy changes along a theta surface different from flow transport. The difference must be a diabatic source. So if flow is moving along, flow will normally move along a theta surface, but if it doesn't, if it moves out of that theta region, or out of that theta layer, then what must be happening? There has to be a diabatic process. If it's cooling, the air will subside. If it's warming, the air should go up across the adiabatic surface. But if it's not, if there's nothing significant going on, it just stays there on that adiabatic surface. So what I'm doing in the model effectively is comparing the expected change of energy to what's actually happening. So I'm putting everything on adiabatic or on isentropic surfaces, and I'm watching the flow on isentropic surfaces. And when I see something happen that's unexpected, like mass increases in that layer or decreases and increases somewhere else, I can attribute that to an adiabatic process. Well, if any of you are familiar with Q1 and Q2, how that's normally done by Charney or Yanai and Esbessenchu, the Q1, Q2. What we do with Q1, Q2 is in a hydrostatic atmosphere, we look for the apparent sources or sinks of energy, and that whole methodology can be extended to here. So what we're going to do in an isentropic layer is if we look at the total amount of entropy in the layer, we have two things. We have a local change of entropy, and then we have the change in entropy going out the boundaries, okay? If there's a lot of entropy exiting the boundaries, then we would expect the local change to be zero unless it's being resupplied by something else. So that when we see, if we add up the local change and the boundary fluxes of energy or mass, we would expect that any change in that thing must be due to an apparent source of energy or mass coming into that isentropic layer. So we can back out how much mass must be entering an isentropic layer by simply viewing how much is leaving that layer out the sides of the domain compared to how much is changing locally. If it's going down when there's a whole bunch leaving, well, that would just cancel. That would make total sense. But if it's not going down and there's a lot leaving, then something must be resupplying it, and that's an apparent source of energy.
And that's in a layer.
In a layer.
Yeah, in a layer, okay.
By using isentropic layers, we can narrow it down very nicely like that. And we'll get into all the math of this. But that's how I'm going to do the metrics.
Is this why your boundaries are important for your modeling scheme? Or is it
Yeah, that's why the boundaries of, well, the two-way nested boundaries on
on the
second
really small grid? Yeah.
Yeah, I'm looking at what's going in and out of that nest.
Okay.
Compared in an isentropic layer, compared to how it's actually changing in that layer.
Yeah.
And what I'm finding is not actually changing much, but there's a lot going out. So there's an apparent source that's just matched by what's going
Yeah,
out.
okay. That's interesting.
So this is the simulation of Patricia with its pressure falling there, and peak surface winds getting up to 90 meters per second. Pretty high. But it was the strongest storm ever recorded in any basin. So these are some of the graphs, and there's so many of them here, but this is apparent isentropic mass source, which is one of the important ones. And I have it in two ways to look at it: pressure coordinate, height coordinate. Pressure coordinate is a little more mass consistent. The pink, or the orange, this orange one here represents the actual total change. And then I have other terms that contribute to that change, being terms that are due just to latent heat release and diabatic processes, including radiation, and then terms that are due to adiabatic transport. In other words, what's going to happen is a plume is going to go up, or the eye wall motion will go up and a certain amount of heating is going to occur, which is going to make the flow jump isentropic surfaces to a higher isentropic surface. But at the same time, the local flow is going to redistribute that increase laterally so that there's no local change or a minimal local change. And then you have the boundary effects. And what's interesting here is the blue represents the, it's hard to resolve it, represents the adiabatic, that's an A, represents the adiabatic process that's redistributing the energy as it enters an isentropic surface. And this is, the green is the energy that's removed from the isentropic surface, and this is the redistribution. When you get up higher, it reverses so that there's a lot of energy entering the isentropic surface here with this green, and then the adiabatic is redistributed. And what you see here between the green and blue is they almost completely cancel each other, right? You almost completely cancel, so there's no local change. In other words, there's flow being produced by the cyclone moving up with latent heating that's filling an isentropic surface with more mass, but at the same time it's being redistributed away, so local change is zero. And then when you look at the boundary conditions, or you look at the total change over the whole domain, including the boundary conditions, you see that the boundary conditions account for almost all the change. I mean, it's hard to get two things closer together than this pink, what do you call that? I guess on here it's kind of a yellowish, I don't know. This line and the pink line, which are the boundary and the actual change, are almost superimposed on each other, up here, but not down here.
Why is it positive?
What's that?
That's the mass, it's a positive mass source on the boundary. Why is it out?
Because you use the opposite sign in the boundary conditions. Because it's the apparent heat source, so you flip the sign. So that an outflow means there's an apparent source. So an outflow would be negative if you took the real sign in the advection term, but you take the opposite sign. That's what's confusing about looking at United's paper. That's what they do. That's how you do it. So you can compare a local change to the what's actually going on at the boundaries. But down here, they don't exactly cancel, but there's very little change. They don't do much. So you can say that if you look at the heating profile, almost everything the tropical cyclone is doing is deposited in this layer. It's not doing much to the environment at all. In between the outflow and the surface, you think of mixing, other things it can do to change the environment, it's practically negligible. Practically nothing. Almost 100% of the energy of a tropical cyclone goes into that outflow. This is looking at it in terms of just Q1 with energy terms like, but in an isentropic layer, all this is the mass flow multiplied by potential temperature times, or the potential temperature times CP, and basically potential temperature is always the same because it's an isentropic layer. So it basically looks exactly the same except the units are a little different for this. If you look at the free energy, this is a little bit interesting. The free energy is down here, this pink line. You can see the free energy source exactly kind of matches the adiabatic source of flow at mid-level. So basically what the free energy is doing is being consumed to lift the parcel to create geopotential, and that's what the adiabatic part is doing in this redistribution. It's taking a lot of the energy and turning it into geopotential, at least the free energy. If you look at other terms like Q2, QR, QMSF, these are specific energy sources, and I got all three of them here. These are what we would typically look at with a tropical cyclone. These would respond to the local temperature changing, the local height changing of the layer, or just the radiative tendency overall. And you look at these numbers, you can get this, kind of some relationship between radiative cooling and the apparent moisture sink. You can look at all those too, and you can think this is very interesting like we've typically done, except for one problem. This is in milliwatts, not watts. The last picture was in watts. This is 1,000 times less magnitude than that mass transport was. So all this radiation talk about, oh, radiation's cooling, it's 1,000 times less than what's going on with the mass field. PV source, that's hard to do, but if you look at the mass source and compare the potential vorticity of the outflow to potential vorticity at a different latitude, like 30 degrees latitude, you find that there's a big negative outflow of low potential vorticity compared to even latitudes further polar from where the storm typically is. This one's nowhere near 30 degrees, but if you look at 30 degrees latitude, it's putting out much lower potential vorticity, and then these things can form plumes of this potential vorticity because the outflow conserves a potential vorticity in the same isentropic layer. So when that moves out, it takes that potential vorticity with it. Well, this is connected. There's a lot of things you can look at here. Work by pressure. We don't want to get into that. I even have turbulent kinetic energy budget here. But if I plot over time versus height of this Q1 term, or the Q mass 1 term, you can see that it consistently stays about the same level of around, this is, in this case here, I think this is 380, 360. Here's a 360. So this one's a little higher than 360. So this is up in the upper UTLS, and it just keeps putting mass out at there. This is above the level of zero net radiation. And this is how much is accumulating in that level. And you can see the same sort of thing if you look at the mass field or the mass output. So I'm just converting these graphs to time plot. And here's the potential vorticity, it just keeps coming out. There's putting more and more potential vorticity up in that layer, and it accumulates over time how much it's putting up there. It's not accumulating like getting lower and lower, it's just how much that was put up there accumulates. But it flows out. So, I did it for all these different storms, and this is just to show you that they all look about the same. This is, this one was the mass outflow, this is the potential vorticity outflow, mass, potential vorticity, mass, potential. These are all different storms. This is the only one I did in the Pacific. Remember Tutu that went over that island, Great Satellite Picture?
Oh, yeah.
Remember that one? It's a little brighter yellow, even in white. Put a lot up, and it's a little higher. If you compare it to Michael, here it's a lot higher because Michael wasn't quite as intense. The pressure wasn't low, so it didn't produce quite as low a theta each. Here's the PV output, potential vorticity. Each one has a low Irma, a little less, but Irma was a little further north. So it went a little bit further north from where these storms are. So it wasn't pushing up as much low PV.
And this is averaged over the grid box.
Averaged, yeah, averaged over the grid too.
Okay.
Yeah. So the boundary term almost exactly matches the total diabatic production. And this happens for each case. So then comes the question, chicken or egg? Is the mass outflow causing the hurricane in the second area? Or is the hurricane causing the mass outflow? They're in sync. The mass outflow exactly balances what's coming up from the storm. Is the storm conforming to a large-scale process that's causing it to happen? After all, the GFS and the ECMWF are pretty amazing in that they can pick up storms before they happen, sometimes a week or two in advance. What's going on?
Jay,
Yeah,
are you implying that the synoptic distribution of PV in the ecotroposphere is dictating where tropical cyclones?
not just the PV, the synoptic distribution of chi, velocity potential, and the movement of chi field like by, let's say, the Kelvin waves, or maybe something else. Here's these boundary terms. Just looking at the boundary terms for each storm, what do you notice?
Of shooting up into the stratosphere.
Shooting up in the stratosphere, and they're tilted upscale in time. So this upward motion that's contributing to these maximums apparently is coming down from above earlier in time. This is an analysis now, this is not a model prediction. Let's look at some more storms. Whoa, that's the diurnal cycle.
What's your top on your model? How do you know you're not getting artificial reflection?
It's just an analysis from the GFS.
What is
I don't know what the GFS is doing, but I know there's a strong diurnal cycle in the chi field because I tried to plot it and I had to filter it out in order to get it to work. In order to look at a good chi field, the diurnal oscillation is almost as strong as the chi field itself, velocity potential. And this is the diurnal cycle in these models. It's coming across. But I wouldn't worry about that except for the fact that it seems to be matching up with this outflow on the tropical cyclones. You know, Jason Dunyan, who's going to have a talk here, will blow his socks off when he sees this, because he's been trying to figure out the diurnal cycle for a long time. Is the diurnal cycle related to atmospheric tides? Because that's what these are.
Do they have different periodicities? I mean, don't they, or?
No, these are just different lengths of simulations. They're all
Oh,
20
okay, okay.
They're all
I can't
exactly
really read
24 hours.
Okay, I can't
And they
read
all
that,
tilt
so,
up
okay.
in time.
Okay.
All of these plots are 24 hours?
No, these plots are different times. Some of them are 14 days or 10
Yeah.
days. So they're over the whole over the whole lifetime of the storm. That's why there's a lot of them. in the storm.
Okay.
But they're all 24-hour cycles. So chicken or egg? Some evidence points to chicken. Like, why is that outflow there? Why, this outflow, in this boundary condition, I've made the second grid bigger to see. And you could put that second grid out to many thousands of kilometers and it still exactly matches the apparent source. So whatever's happening is somehow goes a lot further than the Rossby-Reza deformation. Even though locally you can argue the Rossby-Reza deformation is about 10,000 or more kilometers because of the low potential vorticity. The boundary term is clearly modulated diurnally. And the resonant forcing diurnally propagates downward from above, which suggests that it's there before it connects up with the storm. So the total output integrate over the life cycle of the storm I've done here. This is the total anomalous J, but let me look at the total anomalous mass, which I think is interesting. Total anomalous mass, and this is upper, the red is the upper UTLS and the blue is a lower UTLS. You can see that these are on the order of 15 to 20, up here 15, say 10 to 20 times 10 to the 20th joule or kilograms, which are big units. And this green line is the day simulated. So you can see the bigger ones are because the storms lasted longer. But the kicker on this is this blue line. This is the total amount of mass anomaly in that whole bubble, the whole tropical bubble. In other words, the tropical tropopause is raised because of the mass anomaly. That mass anomaly that's raised in the tropical tropopause is about 23 times 10 to the 20th kilograms. One of these storms, like Tutu here, is adding in 12. That's 50% of how much is in the global available potential energy. So I'll ask the question again. Do these storms matter to the general circulation?
How can they not matter to the general circulation?
This is the apparent mass source compared to the loss of mass at lower levels. When you add these two together, it's fairly small. So they're, but it's still, I think, positive.
Well, the whole mass of the atmosphere is 5 times 10 to the 17th, right? Milligrams?
Oh, that's going to be.
Maybe, I hope so.
Yeah.
I hope I'm wrong.
I mean, from what I'm counting.
The number tends
The,
to-
I don't think so. The potential vorticity magnitude at 356 degrees K looks like this. This is for Patrick, and the pink values are very low potential vorticity. You can see when Patrick forms here, a low potential vorticity plume bubbling out. So you can actually see these outflow bubbles moving away from the storm. Here's the output for Hurricane Irma, which lasted a long time. Look at this bubble forming and extending out, and then extending into the extratropics later on. And here's another one, Maria. Look at that bubble. You can see it forming that low potential vorticity, and then that just pushes out. So let's just look at some conclusions real quick, and I'm not too bad. So one of the conclusions is that almost all the mass and energy that tropical cyclones gather, it's not just latent heating, but it's gathering the potential, the theta max at the surface, in a conditionally unstable atmosphere, is deposited into the UTLS in the form of isentropic mass, and it's not trivial. This outflow layer is neither consistently warmer nor colder than the same layer within the environment around the storm. So it doesn't warm the layer, it doesn't cool the layer, it doesn't raise the layer that much, it just thickens it. So it thickens the layer. Most of the gained mass from this layer of inflation is transported isentropically into the environment. So you build, it's like putting a lot of toothpaste in a tube and then squirting it out through the layer into other layers around it. So there is this equilibrium with the outflow, and the outflow maintains a divergent mass flux that almost exactly balances the diabatic production in the storm. So the storm is lifting air up into that isentropic layer, and then about 100% of that air lifted in the layer is going out in the outflow. So is there a chicken or egg? Does the outflow come first or the storm? I'm going to say for now that there's evidence in both directions. I suspect the outflow comes first, but I don't think I'm conclusive on that at all. And there seems to be an effect of diurnal tides. It looks pretty realistic. But also, there's likely an effect of traveling Kelvin waves. And I think we saw that in Hurricane Matthew, Kelvin waves coming from the west that were causing the air to lift and basically establish that outflow divergence first, and then Matthew rose up in response. So sometimes it's probably fairly certain about what's happening. I don't think it always happens. I'm not willing to say that because I think storms like Maria might have developed their own outflow. A TC deposits a non-trivial amount of mass up there, and it can create localized plumes of available potential energy at low PV that flow across the tropics or can flow into the extratropics. They not only carry available potential energy, but they carry low inertial stability. And low inertial stability is important because it lowers, or low potential vorticity, is important because it lowers the inertial stability and resistance to a storm self-exciting its own divergence pattern. So the lower inertial resistance of a new tropical cyclone's, lower inertial resistance encourages new tropical cyclones to form under the outflow bubble if it remains in the tropics. Tropical plumes flowing poleward destabilize extratropical cyclones because they effectively bring lower Coriolis effect into the tropical cyclone. You're bringing the plume up there with reduced inertial stability, reduced effective Coriolis F. And so this basically can release the cold air and just fall and cause cyclones to bomb and do all sorts of things when it hits them. This is kind of something that what's her name here? Andrea did. She showed that. Also, the lower atmospheric resistance of the outflow that can be plumed into the extratropics promotes widespread severe storms. Severe storms are also limited by the outflow if you have a lot of them. So typically you have 1 or 2 tornadoes. When you see 50 tornadoes, you almost always see one of these plumes coming out of the tropics. The jet dynamics of the emitted tropical plumes also drive the formation of predecessor rain events and other dynamic phenomena in the mid-latitude. Effectively, I think a lot of mid-latitude important weather is derived from these plumes and these effects. Not just from tropical cyclones, but tropical cyclones put an amazing effect up into the tropics that exceeds the Hadley circulation. One thing about the Hadley circulation is that the convection on the ITCZ, except in the Western Pacific, rarely gets up to these potential temperatures. These potential temperatures are 360, 365. It just doesn't get there. Now, some places on the maritime continent occasionally, but it's just part of a plume. Here we got this wholesale conveyor belt of mass just being dumped up there because of the low pressure of the tropical cyclone. This doesn't really occur anywhere else on the globe and for any other reason. So I'll leave you with that. I think it's pretty interesting. That's it.
Sorry, you're right, it's 5 times 10 to the 18th. It is. But I'm curious about your time height section. So a diurnal tide, wave 1 travels westward, 450 meter per second, 27 kilometer vertical wave length. Kelvin waves, 3.5 to 15 days. What was the time scale for your time height section?
Travels westward with what?
Well, the diurnal tide travels westward once a day, so it goes 40,000 kilometers a day. It's a wave number 1.
Well, that would make sense.
Does that fit with the time?
I think the time is just a diurnal cycle from the max to the next max. So a cycle of a wave passing by once every 24 hours would match that.
So people in the middle atmosphere who study tides view these kinds of tropospheric convective systems as all contributing toward driving the tide along with ozone peak. But then you might be right.
I would imagine there's a resonance in that they're
some kind of downward effect of some sort.
they're helping the tides out. Yeah.
These are tide signatures at like 400.
Yeah, and it's kind of noisy in the tide signature in the lower stratosphere.
Yeah, it's really interesting, Greg. I'm thinking that at the edges of the bubble, I'll just take the northern hemisphere as one example. There seems to be a bias toward containing that edge in the tropics, because if the air is squeezed into a thinner isentropic layer, it automatically acquires anticyclonic circulation and it biases it to
Not
coming
as
back.
much as you think, because these are PV minimums, so they don't respond with anticyclonic signatures that well because there's hardly any rotation.
So they go
Almost
in with
rotation.
little to begin, and so it doesn't matter. The stability doesn't matter that much in the conservation of the PV, is what you're saying.
Except on the edges where it's pushing against.
Yeah, and that's what I'm thinking.
Yeah.
That's what I'm interested in, is the edges, because there must be something that differentiates the plumes that really get poleward versus the ones that are kind of
Absolutely.
run of the mill. And what's your guess on what that differentiation is?
The ones that get further poleward interact with an extratropical wave.
So they get carried poleward by
Well,
their interaction.
No, they don't get carried poleward. The extratropical wave lowers the inertial stability on the southern side of a polar jet,
Oh, okay.
which reduces the potential vorticity, so it's more equal, and then that releases.
So it's even the orientation of the wave with respect to the nascent plume that matters.
Yes.
Wow, that's really interesting. So maybe positively and negatively tilted waves are better at escorting these
Yeah,
things
there's something
forward.
going on there, right?
That's interesting. Okay,
Yeah.
that's really interesting.
Yeah, Brett.
So if it's depositing I'm going back to the kernel cycle, where do you get the return, the low-level return flow back into the cyclone to keep the energy going? Because you're showing that it's, and even your PV loops, you can see those things getting ripped way out, and they're coming back in the tropics, but nowhere
There's-
near the cyclone.
Yeah, what I see is that, like I say, the total mass of surface, surface pressure doesn't change a lot. But in between, there's a net mass flux over a deep layer. There's a convergence into the layer over a deep layer. That's not ending up in this updraft. So it's the upper levels that are compensating for this. And, the mass is much higher at low levels, so you don't have to move as much to have the same mass effect.
So the whole larger scale?
Yeah, it seems to be over the lowest, like 500, 600, 700 millivolts below this thing. It's almost all convergence. But very low values. But it adds up to be nearly zero in the count.
So to that question, I mean, some of that mass sinks into the subtropical ridge, right?
Sinks where?
So in the subtropical ridge when these outflows.
I would,
That's what I think.
I would think so. I think it doesn't always exactly match, but if you have somewhat of an excess moving in, that's going to build the ridge because you put more mass up high, which relates to higher pressure at the surface. And so there's some of that going on.
So some of the substance occurs there and then return flow.
It varies. Some storms do more of that than others. But remember, if this is externally driven, we're looking at the chicken here. I mean, there's already a compensating circulation moving across. For instance, the Kelvin wave has up and it has both parts, divergence and convergence. So if this is just assuming the convergence or divergence field of the Kelvin wave, then the convergence field is already somewhere else, and that's where it balances. Yeah.
So what's the expected lifetime of these plumes once they get, once the tropical cyclone begins its demise? You have this residual bubble that's left in the tropics or subtropics. It may extend further into the mid-latitudes. I mean, the notion of it triggering subsequent tropical cyclones or creating an environment for subsequent tropical cyclones is pretty clear, but how long do you think these last? And what's their footprint if you were to look at a season?
Well, I followed them in several instances, and typically they last for 10 days to 2 weeks as a definable entity. And for instance, I'm trying to figure out right now if WUTIP from last week, 2 weeks ago, 3 weeks ago, is what caused that huge cyclone that we had here recently. And I suspect that the outflow bubble that was put into the extratropics by WUTIP, the typhoon, came across, and this is what created that funny storm that hit Colorado and the High Plains. And we know Meggie from 2010 caused that cyclone that we had, because we could follow that. We've done that. That's what I started down on all this about. I also know that in the case of Michelle from 2001, this caused that Algerian storm that I studied. And the Algerian storm that blew up in the Mediterranean is directly related to this. We wrote a paper on this. It's directly related. And that killed 700 people. So it was a lot more devastating than the hurricane itself.
Any additional questions for Greg?
One quick one maybe. In these energy budgets, you're showing mass, primarily in outflow, you're saying it's only outflow, but certainly some portion of the mass ends up in the eye. I mean, because it's driving the pressure falls.
Well, yeah, but that's high theta E in the eye. And so when the storm collapses, it just bounces up and goes up. It goes back up to the top because it's the same. All that really matters was what the entropy of that mass is. And so if you're in the eye and it's suppressed downward, that high entropy, when the storm quits and the inertial balance quits, it pops back up again to its isentropic layer, and it's up.
I'm just wondering when you're looking at, the amount of mass, I'm just thinking about percentages. If any of these energy budgets can show you what percentage of the error.
Is in the eye?
Yeah, we might just play with that.
Yeah, I could do this, I could do this.
It could also be through.
In fact, I do the energy budgets on the intergrid, which is a lot closer to the eye, and they do look a little different before everything calms down on a big average. But you could look at what's going on in the eye, but I don't think it's significant because once the eye goes away, it's all gonna wind up in the big picture anyway. You know,
Is that anticyclonic cirrus outflow that you see, is that tracing this layer of mass that you're talking about?
some of it, but not all of it, because it's not all moist. Not all moist enough to have condensation. So you can see some of the cirrus going out, but not all, it doesn't show the whole thing. And I can trace this stuff, and it gets further and further away, long after the cirrus are gone. So,
So the end of the cirrus is not the end of the mass flow.
there is no end, it just merges into the tropical UTLS.
Okay, well, let's thank Greg one more time.